What's up, guys? In this one, we're going to go over cost functions, substitutability, indirect utility functions, expenditure functions, and in the next video after this, we're going to go over coordination by prices, then I'll do one on trading. So I guess let's get right into it. So the notion of a cost function is that if you're a profit maximizing individual, which we so often assume firms and agents in the economy are, what we are concerned with is figuring out a way to produce something for the cheapest amount we can, for the cheapest cost. So, say I want to produce at least 10 shoes, and I want to do it for as cheaply as possible. That's the notion of a cost function, is figuring out the cheapest way depending on each of the input prices. I have to consider how much the shoelace costs, the leather costs, all the different pieces. And so the way we define a cost function is it's going to depend on y, the amount to be produced. And let me see if he's used P or W's in the past. My apologies. Yeah, looks like he's used W's in the past. So these are going to be the input prices. And here we're considering there are n inputs that you can use and a production function f, which transforms those inputs into an output. So f takes in all of the n inputs and gives you out a specific real number, which is, given all of these inputs, how much is produced? What quantity of your output is produced? So we're considering there are n number of input goods and one output good. And we define this cost function to be equal to the minimum, where we have control over x, the minimum of w dotted with x, subject to f of that x being at least y. And sometimes we will assume that these are all going to be strictly positive solutions, and other times we won't. In those cases where we are not making any assumptions, we would also say x, the vector has to be greater than or equal to 0. And those are going to be our two constraints. And so, more accurately, we can write this as x1 greater than or equal to 0, x2 greater than or equal to 0, and so on. So that means there's going to be n plus 1 constraints if we consider that. So there's this constraint, and then there's each xi between 1 and n has to be greater than or equal to 0. And so then we can use the system we've used before to set up the Lagrangian, and that's really why that math is so useful. So there's going to be, for each x and lambda, we're going to define Lagrangian. And something we'll often do with the corner solutions is we'll give them their own multiplier. We call it mu, but you treat it basically as another one of the lambdas. So for this one, we'll do that. And xi greater than 0 for all I. So we'll use just the single value lambda for this constraint, and then we'll use mu for each of the non-zero constraints. And so this function is going to be the objective function plus lambda y minus f of x plus mu, the vector, dotted with negative xi. and that comes from these are considered our b's, and so we do b minus whatever's on this side. And so you could reformulate this into minus and a positive. There we go. That's the way we set up Lagrangian. And then you apply the first order conditions as we have before. So we're going to have for all I equals 1, 2, up to n, you have the partial derivative of the Lagrangian evaluated at the optimum equal to 0. Then you have the partial derivative with respect to lambda, and there's just one lambda now, so we say partial of lambda, or the partial derivative of the Lagrangian at the optimum with respect to lambda is going to be less than or equal to 0. In this case, that's because this inequality has to hold less than or equal to 0, so f of x is bigger than y. So that's why we do it that way. We're going to say this is less than or equal to 0. We're going to say lambda is greater than or equal to 0. And we're going to say lambda times the partial with respect to lambda is equal to 0. I'm going to do the same idea with mu, except this time it's now going to be for all I between 1 and n as well, because there are going to be n mu's. So we can do that up here. We say partial L at the optimum over partial mu I less than or equal to 0, mu I greater than or equal to 0, and mu I times the partial L over partial I, or mu I, is going to be equal to 0. And then we walk through these conditions depending on the function that we're given, and we solve for the candidates for optima. So that's how cost functions work. Not going to walk through it as explicitly for the consumer demand stuff because it's really just looking at these problems and applying the Lagrangian and the Kuhn-Tucker first order conditions. So now we look at consumer demand. And now instead of considering a firm minimizing costs, we are considering an individual trying to maximize their utility. For this, we make an abstraction that we can think about human preferences in a function that will rank what they like. And this is where that idea of an indifference curve comes into play, because there's a lot of geometric intuition behind this. Yeah. You know what, before we proceed with consumer demand, I want to give one more thing on cost. So essentially, what we can do is we can look at all the different ISO quant lines. We'll say this produces, 10 output, and we'll say, this one produces 5. And of course, there are lots of different curves we can draw. And so now we're considering that there are only two inputs, x1 and x2. And so depending on the W's, we can draw the ISO cost line. So the ISO cost line is going to look like this. And it's basically we spend the same amount. So it's for some kappa, the cost, it's going to be equal to W1x1 plus Wx2. So we say x2 equals negative W1 over W2 times x1 plus k over W2. And we can draw that line like this, depending on the value of kappa we pick. So if our constraint is that we have to produce at least 5, then we have to be at least on this curve, and we want to bring in this cost line as close to the origin as possible, because as you go this way, your kappa is decreasing, you're spending less. So that's going to occur where there's this tangency, and that's why we care about the derivatives. Now, obviously, if your function is not differentiable, it's better to consider it using intuition and trying to draw it out than it is to try and do the calculus. But this is why that tendency holds, is because you're wanting to bring down your cost line as close as possible. Now, very, very similar intuition exists for this consumer demand stuff, but I will omit it for the sake of time. that's what the angle he's focused on, and so I'm going to focus on kind of the algebraic angle. So we define indirect utility functions. We define it as usually V, and I'm going to see, sorry, again, if he's using P's or what parameters he's using here, just so I keep on the same page. Yeah, it looks like he's going to use the vector P and the amount of wealth W. So P here is how much each good costs. W is the amount of wealth the person has. And we're going to define this to be equal to the maximum, where we choose x, of the utility function at x, subject to not spending more than we have. And again, you can introduce the x1 greater than or equal to 0 constraints like this, or you could multiply them by negatives and flip the inequalities so that they all go the same direction. And then you put this in the Lagrangian as before. This guy is the amount of each one you're buying, the cost of each one, that dot product, the sum of how much you spend has to be less than the wealth you have. We call this an indirect utility because it's assuming we're picking the optimal consumption. It tells us what quantity of utility we get for some prices and wealth. Now keep in mind, utility functions really only are able to rank preferences. They're not so much able to tell us, I am 10 happy. That doesn't really mean anything. You are double as happy as me. That doesn't really work that way. So now expenditure functions. Or actually, before I do that, I want to touch on monotonic transformations. If we have a function phi, which takes in a real number and gives out a real number, is greater than 0, then if we replace our utility function with phi of u, gives the same preferences. It will not give the same final value of utility in most cases, but it'll give us the same optimal choices of x. And I've proved this in a few of the SI sessions before. Essentially, you can see that yourself by replacing that in the FOCs and showing that it's going to just give you the same result. So the intuition there is that as long as you are doing this by something that's positive, its derivative is positive, it's an increasing function, so you're keeping the ordering of preferences the same. So that's this result about indirect utility. Now, expenditure functions. These guys we're going to write using E, and now it's going to be Y and W. This is going to be amount of utility. This is going to be prices, or I think I used P, sorry. Prices of goods. And we're going to define this as the minimum cost way to be a certain amount of happy. And again, you could introduce your non-negativity constraints if you so choose. And so the intuition here is we're finding the minimum amount we spend subject to getting a certain amount of utility. This allows us to see things like inflation adjustments because now we see if the prices change, how much we're going to have to spend to keep the same Y we had before. So that's this idea of an expenditure function. And both these and the indirect utility can be solved using either the same graphical intuition if it's not differentiable, or the Lagrangian. And that's kind of how we touch on consumer demand, expenditure functions, and indirect utility, and on cost functions for firm behavior. And the way that we figure out, for example, the cost function is we take this optimal x and plug it back in to the function itself. We take the optimal choice and see how much we're spending. To figure out the indirect utility, you take this optimal x and plug it back into u. To figure out the amount of utility your optimal choice gives you, to figure out the amount you're spending, you take this optimal x and plug it back in to see how much you spent. That's this idea of applying the FOCs, and why I hammer it so hard is because most of the stuff we do in the course comes down to the Kuhn-Tucker conditions. Hopefully this is helpful. In the next one, I'm going to try to cover coordination by prices, then I'll do one on trading, and that should do it for the exam review. Yeah, thanks.